Hey guys, we were going through syntax and semantic of the compiler phase. So last time when I just gone through the when I rewatched the video, I think I didn't express, I didn't like programmatically I have written so much, but I couldn't explain it better in previous video about parsing of expression. So we'll revisit parsing of expression and we'll go through with the block statements, if block, else if and else blocks. Okay. So starting with no, let's start with the same example. Let's go through two examples. One is this 10 plus 10 plus 10 into 2 and 10 plus 10 into 2 plus 10. So these two will evaluate into same in C, right? But the expression trees are going to look different. So let's go to that. How it will be. So left is equal to parse primary. So parse primary is always going to get the number, right? If you look at here, it's integer or identifier we are going to make. So parse primary is always going to be an atomic element, right? So this is always going to return either an identifier or an integer. So in our case, if it was instead of 10, we had A and A. So it's going to return A or that 10, right? So let's go through this example first. This case left equal to 10. And then right after that, we have operator token. Operator token is going to be directly represented by operator OP equal to 10, and the rest part is going to be my right. Right is equal to this. Okay, this is my right. This is my right portion. Okay. Now, the main stuff here is, see, before this loop, I have left. Okay, and I have to iterate through the entire tokens because there might be a case where this is the only statement that I have in my language, in my code. Okay, so in that case, I have to evaluate for this, right? So for that reason, I have to go and iterate through entire tokens. Okay, so that's why I have this external value, and then okay, I'll reach that after this. So I have left equal to 10, then my operator, which is plus, then after that 10 plus 10 into 2, this portion. Okay. Then if you look at next what we have, next we have to evaluate this, right? So we are creating a binary expression tree. In that the left portion is this, and the right portion is whatever gets evaluated over here. This one, whatever result gets evaluated, that will be the right portion. So for that, before we go into evaluation, we have a recursive call to parse expression, right? So that should be solved first. So if you look at, we have a precedence over here. Now this precedence will play an important role. So this precedence for multiplication and division have given 9, the highest precedence. Now after that, just the precedence lower to it is addition and subtraction. So and one more thing what I have done here is I am giving higher preference to the older plus. So if we look at this expression, we rename this plus as plus dash and this one plus double dash. So what I'm doing here is plus plus dash preference precedence is greater than. So I am doing this so that I get to evaluate quickly for this, right? So 10 plus 10 is 20. So I quickly have the result for this. So I don't have to wait much time, right? So quickly I'll have this result as 20. Then I can go for further evaluation after evaluating for this because multiplication has higher precedence than plus rate. So yeah. So main thing is for older operators, I'm giving higher precedence than the. So if so, let's say I have two operators, same operators or same level operators. Let's say instead of this, I have minus. Minus is also at same precedence rate. So I have set plus and minus as same precedence rate. It has precedence of 8. So in this case also I give this plus a higher precedence than this minus. So this gets evaluated to 20 and then I will evaluate for this. So that's what is done here. I am looking for the precedence. I'll look for the precedence. In our case it is 10 plus this one, right? So I look for the precedence. So the precedence here is if you look at here we have this plus, okay, plus we have right now we haven't reached at this plus yet. At this line, left is equal to 10 will get returned. Left is equal to 10. After that, operator is plus. After that, right is 10 plus 10 into 2. So if you look at uh, before here, we came over here, right? This where we decide on the precedence. Minimum precedence is initiated to 0. So this call which I made, so this call is made in parse variable declaration, also in assignment statement. So here also you can see it is given 0. Then then what else? Then in parse exit statement also minimum precedence is set to 0, defaulted to 0. Parse if also defaulted to 0. Then parse exit, parse if, parse else if, and this would be parse do while, then this parse do while, okay. Parse while statement, parse while statement. Yeah. Then next, so everywhere I have given the default value of min precedence to 0. So that's my starting point. See, parse expression, parse expression. So so initially we are having only plus and plus uh, the this one get precedence of plus. This is going to be equal to 8. Okay, this is going to return 8. So precedence is 8. Is 8 less than 0, which is not true. So we are not going to break out of the loop. Then we go into right. So right is going to recursively call parse expression. So again, we'll go to parse primary. So what has happened right now is we have this 10. Okay. At left, we have 10. At left, we have 10. And at the root, we have this plus. And then this right, we have this expression. Okay. This is what we have. Then this is recursively calling this function again. So again, left is getting assigned. Left is getting assigned to 10. Okay. So left is equal to right now. Left is equal to at this level of tree. Now this portion is getting divided. This subtree. This is what we are evaluating for. 10 plus 10 into. So for this left is 10. Operator is equal to plus. This is the operator, right? So we'll increment and come to the operator. Then next we have, next before going to the right, we'll check the precedence. So previous precedence was 8, right? So 8 plus 1. So remember I told you that just now I told you that precedence of this one is greater than this one, right? So to maintain that, what should I do? I'll just add plus one to it. Okay. So this operator, this one. So let me mark it as this one, and this one. This operator is double dash. Okay, this double dash. Okay. So this double dash operator, its precedence is 8. It's fixed, and this plus single dash is going to return as 8 plus 1 9 over here. Now we have uh, precedence is 8. 8 is lesser than 9, right? Because minimum precedence is passed from the previous one, right? Previous one is what? This one will get returned. So its precedence was 8 plus 1 was returned over here. So 8 is less than 9. So we are going to break out of this loop. So when we break, we are not creating the tree. We are not creating the tree further. We are stopped at this level. 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 Then what we do? Then what we do is here, as soon as we break out of loop, we are going to return the left portion. So the left portion is going to be what? Left portion of this tree is what? See, left portion of this tree was left is equal to 10. OP was operator was equal to plus. Before right, we are doing this addition, right? We have to make the decision because see that right is going to create a tree. So before creation of the tree itself, we have to make a decision. So here itself, we are returning left portion. So what we have done is we are just returning this portion, this portion, and we have pending with this. We are pending with this plus 10 into 2 is pending. Okay. So this is what will get returned. So here, if you look at, it will come back to this location. So the previous one we made a recursive call, right? So that recursive call, when it gets returned at this right, it the value is going to be this node 10. That 10 is returned now, and we are pending with this. Okay. So then what we do is we are going to create this binary expression tree. So in this binary expression tree, we just create the left portion as the left, which already we have this plus this 10, and the right portion is going to be this 10. Okay. And then we evaluate for the result. So uh, yeah, here I just make a quick double check. It's a double check, to see whether both of these are integer literals. Only then I can evaluate, right? Because if I have to evaluate this 10 plus 10, I can't do this way, right? I can't have it like 10, like the previous case. I had 10 plus this one. So this is a tree, right? This is a subtree. So this subtree is not integer literal, right? So I can't add integer literal with a tree. It has to be both should be an integer literal. Only then I can add it. So for that reason, I'm doing a check here, and also I'm doing a check here, a double check, so that until I reach the root node, leaf node. So until I reach the leaf node, and uh, and the leaf node has to be the integer literal. Only then I'm going to perform the particular operation. So this is going to just return this one left plus right this portion. So left plus right, and basically it's going to return the integer result of 10 plus 10, which is 20. So this 20, this would evaluate to 20. Okay. So as you can see, it's a static int, so it's going to return integer. So that result would be returned, 20 is returned. Then I'm creating a new folded node. Okay. Folded node is the result after the constant folding. Then creating node, and then so same thing. I'm just setting up the operator tokens line and column. Okay, as the line and column for that particular node. Then finally, I set in the result that value dot int val. Remember, the value was a union, right? So the value is a union of integer value and string value, because it can be identifier or integer literal. So for that reason, if it's integer literal, just I can store as an integer variable. But if it's identifier, I need to store the identifier name, right? So for that reason, char star. So finally, folds value dot imply will have result, right? The final evaluated result. So which was 20. 20 would be stored into that folder node, and then we are just going to delete that binary expression because we don't require it anymore. So the left portion and right portion we are setting it to null, and just freeing that tree. And left portion we are setting it for. Yeah, remember this left here. This left is set over here. Okay. See what we always require this, right? If you see my code, it's always left operator, right? Right. This the result, and this result would be stored into the folded node. Folded node would have this result, left operator right. So here initially I have set left is equal to parse primary. But inside this loop, I don't have left, right? So that left I'll be compensating over here. This folded one, I'll be setting it. So this left equal to folded, which is this 20. The node 20 will become my left portion. So finally, I'll have left equal to 20 and I have this pending, right? This was pending. This portion was pending. So this portion is pending. So that's what will come here and resolve in this portion again in the while loop. So again in while loop, we will have operator equal to plus, and then we have operator is gone, right? So right is equal to we evaluate this. So now another very obvious question is like now how do we come back to this portion, like how do we remember we have to come back to plus 10 into 2. So that's a very easy thing. If you look at parse primary, we have this pointer to I. So everything in this I pointer is what would increment, right? So for parse primary, we are for integer, literal, and identifier, we are just incrementing it by one and just returning the node. Okay, that node. So in that node, we'll just create the node and send the token, send that particular token, and it's made. And if the most important part is we are incrementing it by only one. So that's why parse primary. So here previously when we went to right portion, when we had this entire thing, we went to we'll again call this left, right, then we'll call the right, but we didn't go to the right portion because we had the so we had this one, right, this one. So this precedence greater than this one. So for that reason, we broke out of the loop and we just evaluated for this one, this 10 plus 10. And why am I doing this? I'm just quickly evaluating for this 10 plus 10 rather than waiting for entire tree, building of tree. So quickly I'll just evaluate for 10 plus 10, which is 20. Then I can move on to next evaluation. So building the tree would take even more time, right? So I'm just uh, evaluating right after I get to know the precedence and my operator. So that's for quick evaluation. Okay. So that's why we'll remember that we have to evaluate for next plus 10 into 2. So it's from here, from parse primary, we get to know that we have to next go into plus 10 into 2. Yeah. So operator is right now, so we have left is 20. So left is 20, how? Because of this folded. So I just kept double check if we are unable to remove that binary expression subtree. So I'll just set that left portion as binary expression tree if I'm unable to fold. Mm. So usually I'll be able to fold, but just in case I kept else condition. If it's unable to fold, I am just taking out that entire subtree. This subtree, that 10, I had that 10 plus 10, right? That would be set into left. So that binary tree set to left, just in case if I'm uh, unable to remove that binary tree. So now we have uh, operator plus, right. So we have this way 20. Yes. This is my tree right now, and for this one I have to further go into, I'll be going to recursion, right here. Right is equal to parse expression, so it's a recursion. So as for this portion, 10 into 2, here left equal to 10, and operator equal to this one. And will we break out of the loop? So that's what we have to see. So previous operator was plus, and its precedence is 8. So 8 plus 1 is 9. Okay, 9. 8 plus 1, because I'll be adding the precedence to the precedence, I'll be adding 1, right? Why I'm doing that? So that the older precedence, no, I had told, right? This one again. So precedence of plus single dash is greater than plus double dash for that disk. So 9 and precedence of multiplication is also 9. So is 9, which is current precedence, is it lesser than the previous precedence 9? So that's not the case. So I'll be in this loop itself. So right is going to be 2. So the subtree is going to be, this subtree is going to look like this now. 10, this multiplication, then this 2. Now as soon as when I go for so again it's a recursion, right? So parse expression, again I'll go into left. Left is equal to parse primary. So parse primary, I'll get 2 back. So I have reached the end earlier, right? I have reached this end. So I'll not come into the while loop. I'll just return this left. I'll just return this left. So when I'm returning the left, I have to come back to my previous state, which is left and right. Left is equal to 10, and this operator is multiplication. So binary expression, it's left is this 10, and its right is going to be 2. And I have to fold it also as well. So and its root node, the binary expression root node is going to be operator token, which is this multiplication. Okay, and folded reset. So when I fold this 10 into 2, so this result, this result is going to give me 20. 20. So this and finally this 20 is folded equal to 20. This node is created, and finally left equal to fold. Okay. So and that left is what I return. So finally, after returning, I'll have this one, right? I'll have 20 and this 20. Finally, here, uh, the final expression would be 20 plus 20. And again, uh, and again in folded, this evaluation would result into 20 plus 20 is 40. And then into folded, I have 40. Okay. So into folded, I'll have 40. Then that would be set into left. Left is equal to folded. And finally, that would be return left. So finally, this 40 would be returned. So as you can see here, we are evaluating 10 plus 10 first. Then after that, we are waiting for 10 into 2 because it has higher precedence, right? Multiplication has higher precedence. And after that evaluates only, we are going for 20 plus this 20. Okay. Now let's go through the next example, this one, for a clear understanding of things. So in this case, it's the same, left equal to 10. Here operator equal to plus. Okay. And here right is equal to right is equal to 10 into 2. Yeah, 10 into 2 plus 10. Okay. And it's going to be a recursive call. So before the recursive call, I'll have 10. My right subtree. So as for 10 into 2 plus 10. So here left is going to be 10. Operator is equal to star. Now before going to right, previous operator was plus. So it was having precedence of 8. 8 plus 1. Okay. This is going to be my min precedence. This is going to be min precedence. Okay. So min precedence is 8 plus 1 and the current operator is 9. Is 9 lesser than 9? So that's not the case. So uh, we are going to set right is equal to 2 plus 10. So I have now this my subtree right now 10 at the left. Then operator is here multiplication. Then this 2 plus 10. Okay. Then what we do is here we have right is equal to parse expression, right? So it's a recursive call. Again, left is equal to 2 and operator equal to plus. And again, now it was multiplication, right? Multiplication's precedence was 9. Okay, 9 plus 1. This is what is passed, right? 9 plus 1. So min precedence becomes 9 plus 1. So 9 plus 1 is it greater than this plus operator has precedence of 8. So is 8 less than 9 plus 1? 10. So 8 is less than 10. So we are going to break out of the loop. So when we break out of the loop, we have to return left. So when we return left, what are we left with? So when left equal to 2 is returned, this portion is still pending. Right. So left equal to 2 is returned because see this portion right is equal to 2 plus 10 was there, right? So we had right is equal to 2 plus 10. And here we are returning left. So left is equal to 2 will be returned. So right now we have this portion pending and left is equal to 2. So left is 2 which is set into, see, left is equal to 2, right? So at left equal to 2 which will be going into right. So finally we are only having right is equal to 2 when we return to the upper level. Then finally here we do the folding, right? In folding we evaluate for the expression is 10 into 2 which is going to be 20. It's going to be 20. Okay. So 20 is evaluated, right? 20 is evaluated for this one, this entire thing. 20 is the result. As in, when we go to the even upper layer, one more layer up, so 20 is returned. This right is 10 into 2 plus 10, right? Now here we return 20. Here we return 20. And again, still plus 10 is left. Yeah. So here we return 20. So this entire thing would become 20 now. And then again, we are going to, as soon as we have this, we are going to fold it, right? So when we fold it, it will become 10 plus 20 is going to be 30. Okay, 30. So, and still we are pending with plus 10. Okay. So right now what we have is 30. 30 is what we have. And pending is what? We have pending plus 10. So again, left is equal to 30, operator equal to plus, and right is equal to 10. Okay. So this will start as a new expression. So 30 plus 10 will start as a new expression. So our this portion, this mean precedence is going to be again 0. Okay. So in that case, our tree would be this way, 30, mm, 10, and finally this would be valued to 40. So both are same. So you can see the difference here. We are now evaluating for, we are for 10 plus 10 into 2. We are waiting for the result of subtract 10 into 2. Only then we are adding 10 plus 20. Okay, this is a 10 plus 20. And after that 10 plus 20, we are evaluating to 30. And after that, we are adding the result into 10. But here the difference was we'll do 10 plus 10, which is 20. Then 20 plus, we'll wait for this evaluation to complete, which is again at 20. So 20 plus 20. So final tree was 20 plus 20. But here the final tree is 30 plus 10. Okay. So that's the difference.